All right. Hi, everyone. Today we're very happy to have John Carrasco visiting us from Northwestern University. He got his PhD at UCLA and then went on to do postdoctoral research at the Institute for Advanced Study in Stanford. And then since then, he has held senior positions at Saclay and now at Northwestern University. He will tell us about gluons for nothing, gravitons for free. Thank you so much. Please.
Of course. All right, well, it's a tremendous pleasure to be here in Purdue. I overlapped with Nima at Stanford for a year, and so I think this is maybe the first time we've seen each other since then. Yeah, no, but this is spectacular. It's such an easy train ride away from Chicago. So if any of you want to visit in Northwestern, also reach out. Okay, good. So I am, let's see. All right. So one thing I've started noticing, so I do a lot of research in scattering amplitudes and relativistic quantum field theory. And one thing I've noticed that us as a field have started to do is when we give talks, especially to broader audiences, they'll start with an excuse slide where they talk about the limits of their analysis. Oh, it's only going to be in planar, only like maximal supersymmetry, that type of thing. Now, my excuse slide is phenomenologically no excuses, that our ambition is to go everywhere. Finite color, awesome. Finite color, d dimensions, masses, supersymmetry, UV completions, cosmology, holography, resummation. We really want to take the structure we're identifying in some cases, very simple places and generalize, and that's where we're going. This is a theory talk. It's not an experimental talk. And it's really about learning a new language. By listening to the predictions of relativistic quantum field theory, we discover a language that lets us elevate putative analogies between gravity theories to sharp dualities. We have every right to ask questions of gauge theory systems towards understanding what puzzles are deeply gravitational and which are in some sense universal, to leverage strategies between communities. And so this type of game lets us really spend time talking with lots of different people. And I'm going to give examples of this as it comes up, but just to make it very clear. I don't know. How do I hide this thing?
If you just move yours, yeah, we'll go down.
It will go away on its own. All right, so good. So this is gonna be very prediction oriented, and we're gonna be talking about what we can learn from scattering amplitudes. And again, this is just the overlap between initial states at past infinity to final states of future infinity. And the reason, besides this being useful for all sorts of phenomenology, that we love to study this to understand structure, is because it's something we have a right to understand, something that is gauge invariant and something that's field theory definition invariant. And this gives us a lot of power, because if we find another way of telling stories that explain exactly the same predictions in these theories, then but is of a different computational class in executing, then we've actually identified structure that makes our lives better, right? And so this is what I'll be talking about. All right, so the takeaway that I hope you leave this talk with, the end, is that amplitudes are great for learning about theories, they're great for relating theories, and we can actually make these structures manifest at the level of quantum operators describing the theories, so that we can talk with our friends who don't necessarily actually appreciate scattering amplitudes per se, but might be deeply interested in these structures. Okay, so my title is double copy. So there's this familiar story, which is we have every right to add relativistic quantum field theories together. And what I mean by this is we've got theories that are completely consistent with some particles doing stuff, completely consistent with other particles doing stuff. And of course, we can let them interact, right? We allow an interaction. In some sense, we've added our theories together. And we get predictions now from this theory that contains all of these things going together. What I'd like you to leave this conversation we're having today is the notion that the calculus of theories is richer. You have every right, in some sense, to be taking products and factorizing. This is what goes under the rubric of double copy structure. And today's talk is going to be very pedagogic at the level of tree level, and we're going to see how this structure emerges. Okay? I will say that the literature here is vast. There are now a tremendous number of papers discussing this in various contexts. I've listed a few reviews that run the gamut from very accessible to broad audiences to particularly technical engagements. Okay, so the question we're going to address in a large part of this talk is how to find Einstein gravity from considering interactions of massless vectors. And the way we're going to get there is we're going to talk about fields and the local symmetries we're going to demand. We're going to start by defining our fundamental fields in a free sense, so free vectors like photons and free gravitons, and their associated free symmetries. We're going to demand that these symmetries persist even for our interactions. We're going to start introducing interactions, and we're going to restrict ourselves to interactions that still admit these free symmetries. But we're going to look not at the level of the operators themselves, but on things that are very, very clean conceptually on-shelf physical scattering amplitudes. And step by step, driven by the symmetry, we'll naturally build up the nonlinear interactions essential for Yang-Mills and gravity at the semi-classical level. So extracting a series expansion of Einstein-Hilbert around an asymptotically flat space-time in terms of these operators, just from these considerations. Okay, so where are we going to start? We're going to start with vectors. We'll start with something super familiar, I hope, to all of us, linearized gauge invariance. And as you probably remember from your first classical field theory course, this completely fixes the quadratic term in the action to something that looks like Maxwell's action, F squared, right? Up to total derivatives, field redefinitions. Good. This completely fixes a propagator, right? And we can write the propagator in terms of a physical state projector where we're just summing over the states and across. And I've written down this projector. So we'll be using it a little bit as we start building up from lower multiplicity to higher multiplicity amplitudes, right? Some features that I'd like you to just remember is what these polarizations are doing for a living. These are just encoding our states. Our polarization vectors completely encode our states. We know in 4 dimensions that we only need 2 polarization, only 2 physical states to span all of them, right? And we can tell this just by grabbing sunglasses, 2 polarized sunglasses. We completely block our light, so nothing's getting through once we've oriented like this, yeah? Of course, we're talking about quantum, right? And this is actually something you can see with three sunglasses by sticking in a middle guide to third and rotating it 45 degrees. Then you actually start getting some light through. Yeah? Okay, good. And the point is, we have every right to be talking about our free states in terms of just momentum and some small set of polarization vectors, right? In d dimensions, d minus 2 physical states. Okay, good. All right, so from sunglasses to LEGO, yeah? You consider just the simplest generalization from spin 1 to spin 2 for your gauge invariance. So now your parameter, right? It's no longer a scalar field, now it's a vector field that starts to get varied, right? And this is the linearized diffeomorphism for gravitons that are not interacting. Yeah, and this completely fixes quadratic terms in Lagrangian, linearized Einstein. Again, up to total derivatives or field redefinitions. The propagator, you'll notice you can write exactly in terms of the gauge propagators I wrote before. So here's some propagating tensor, right? Taking from here to here. You'll notice this removes, so in four dimensions, how many physical states does a graviton have? Huh? Two, right, as two, right? So two squared is not two squared is four, right? So you have to remove anything that's antisymmetric, you have to subtract out the state, right? It's just subtract out the trace. And then you're left with graviton states. Okay, good. Right, so two physical states, the 4 dimensions. One thing that's spectacular is this like d over 2 times d minus 3 physical states in general. You can completely specify in terms of the vector polarizations, so long as you symmetrize and remove out the trace. Yeah. And so we have every right to be talking about free gravitons in terms of the momentum and 2 polarization vectors. Right. And then we've specified our free graviton state. Good. So that's it. So that's all we're starting off with. It's just these linearized symmetries, the symmetry as we have any interactions, where we're just projecting out stuff that's unphysical. Yeah. Okay. So where we're going now is we're going to use these symmetries, right, to identify what possible interactions we could write down. Where we're gonna let 3 vectors interact, we'll let 3 gravitons interact. We'll see all the different ways we could write it down. But it turns out there's not very many at all. It's very, very, very constrained. It's constrained by the on-shell kinematics of 3 particles interacting. What we'll find is that the Ward identity demanding gauge invariance forces antisymmetric kinematics for our 3 vectors, right? The vectors are bosons. And so we either have no interaction or we need to introduce additional quantum numbers to eat up that antisymmetry. Right? This is going to lead ultimately to what the structure constants are, the Lie algebra of the gauge theory. Right? Again, for the graviton, the Ward identity Bose symmetry is completely, so the linear isomorphism here is completely satisfied by the same vector kinematics we bring here squared. And we'll see how this shows up. All right, good. Good, so look at our building blocks. So we're trying to write down the space of scattering amplitudes at 3 points that can describe vectors interacting. That's the game. But we don't have a lot of Legos to choose from. We don't have a lot of building blocks because our scalar Mandelstams vanish for on-shell kinematics for massless particles, right? So we only have 6 blocks. Like we can let our polarizations talk to each other. We can let our polarizations talk to momenta, but there's redundancy there, right? So you really only have 6 building blocks you can bring together. All right, so that's the game. Just what can we write down? What's the rule? The rule is that particles of spin s must have s polarization per term, right? Good. So you try general ansatz up to a single derivative, right? Mirroring the structure we had for our linearized gauge theory for a single derivative. The only non-vanishing combination of kinematics as gauge invariant is something that's manifestly antisymmetric. You exchange any 2 particles, you get a minus sign. So we need something else. We need some sort of additional quantum number internal indices yielding antisymmetric f's, something antisymmetric if we want a non-vanishing 3-point amplitude between these theories. All right? Otherwise, this is 0. This is the only thing we can write down. Now you can say, what about higher derivatives? There's one more thing you can write down, right? And it's just a polarization dotted with a momenta, all 3 of them just together in one expression, that yields your trace f cubed. That's the only other operator you can write down that you can't get rid of by field redefinition. Yeah, that's also antisymmetric. So that would also need these numbers, right? Okay, now I'll point out that that doesn't mean what we've landed on is a Yang-Mills theory. It doesn't have to be a Yang-Mills theory yet, right? It doesn't mean, right? So this is where we're going. This is what we need to have at the end of the day for us to have landed on Yang-Mills, right? We need these additional quantum numbers to satisfy both antisymmetry and then Jacobi identities. Then they get to be, structure constants for a Lie algebra, right? That's not what we have right now. Right now, we found this, but we've only looked at 3 points. So there's no point for this to have shown up yet, right? And we'll see this is forced on us at 4 points. We can't get away from it. Okay, good. So we've got the only vector amplitude we can write down with a single derivative, like derivatives turn into momentum, single momentum. Yeah. Now we can get to go to gravity. You play exactly the same game. You try a general ansatz, you're building blocks with two derivatives. The only non-vanishing combination of kinematics that satisfies the linear diffeomorphism is this guy right here. All right? This is manifestly both symmetric, it's great. I hope you notice that it's literally two copies of the vector kinematics we just wrote down. All right, so it's the first non-trivial double copy. So we had this sort of double copy structure for the free states where we got to write the polarizations of the gravitons in terms of two copies of polarization vectors. But we're seeing this emerging for interactions as well, right? Okay. I want you to contrast the simplicity of what I just put on the board with the off-shell re-graviton vertex and the Donder gauge. So this is first written down by DeWitt in the late 60s. It's a mess, right? But if you go on shell, right? If you impose on shell conditions, then it all collapses, right? It's just the product of these two gauge building blocks, these two Legos snap together. Great. And so you can read off the operator, a gauge fixed, a particular version of the operator needed to reproduce this. Of course, you can add zero, an uncountably infinite number of ways to any action, right? But as long as it manifests this, then you're cooking in the theory that can produce this, right? Doesn't mean it's a consistent theory at all. Yeah. If I just linearized gravity, that's linearized gauge invariant. If I just add this term, I'm not done, right? I'm done up to this order, but then I'll have inconsistencies that show up at higher multiplicity that I need to address. Okay. Good. So let's go to all interactions. To go to higher point interactions, we're going to play the same game. We're going to come up with the Legos we can write down. We're going to snap them together, and then we're going to impose consistency conditions, right? Linearized symmetry, but also something that's crucially important, that we're talking about the same theory that we mentioned. So there's a consistency in factorization, right? And this is actually exploiting this true thing that if I choose my kinematics so that internal lines go on shell, all that can be allowed to cross the theory are the physical states of the theory. And then I can write it in terms of a product of lower multiplicity amplitudes summing over the states with my physical projectors. Yeah? Are people with me on this? This is exactly how we go to high loops. So when we do like 5 loops in maximal supergravity, right? It's using this structure rather than, the horrendous mess, as you saw what the off-shell Feynman rule looked like, right? It's a tremendous mess. But when you write things that are physical, that are gauge invariant, like these individual pieces have to be after I go on shell, right? Then I'm dealing with very compact expressions. I'm not carrying around this tremendous redundancy of unphysical information that needs to collapse away every time I assemble to something actually physical, like a complete amplitude. Yeah? So even though I'm staying at tree level, we're approaching tree level exactly the same way we approach multi-loop calculations these days. All right? Good. Cool. So we're looking at 4 points. We're looking at 4 points. And so in general, in 4 points, right? I'll have whatever contributing that has factorization channels. And maybe I need to add some sort of putative contact term, some 4-point operators showing up. There's some 4-field operator that's contributing. Yeah? Okay. In terms of my scattering amplitude here, I can always take this, whatever it is, and assign it to my cubic graphs by using very sophisticated, S over S equals T over T equals U over U equals 1. This is just bookkeeping. I'm not doing anything super strategic but what this lets me do, for example, and we'll see the power of this as we go to higher and higher multiplicity, is we start putting theories that in one way of writing them would involve, greater and greater contact terms on the same scaffolding, where we just have to look at the structure of the cubic graphs, right? We're encoding the contact terms into how we're dressing the cubic graphs. But now we actually have a right to start comparing theories on a sort of graph by graph level. All right? Everybody with me with what we're doing here? I mean, it's just bookkeeping, nothing super fancy. All right. Good. Now, so besides demanding linearized diffeomorphism invariance, we're demanding consistency. So for example, we consider just the S channel cutter, just cutting this graph, putting its internal line on shell. Its residue, right? Its residue, here you go on shell, has to equal the sum over states of the 3-point amplitudes with the associated momenta after I project only to the physical states. Right. So if I was doing this strictly in 4 dimensions, I could literally fix helicities for these guys and then see what helicities can cross my cut. Right. But in general, I'm doing this in D dimensions, which is why we use this D-dimensional state projector. It's just completeness. Right. By the way, I mean, so this method of perturbatively constructing things that manifest only physical information crossing cuts when you go on shell. This goes under the rubric of unitarity method. So maybe you've heard of this, generalized unitarity towards, you can use it both to verify your multi-loop integrands. If I hand you, so this is the integrand at 5 loops for this special theory, right? There's a verification procedure. You can check to see if it satisfies the cuts for that theory. Are only the particles I think about crossing the cuts? Or do you have other information? Or are you missing information? Right? But anytime you have something that's verification, you can invert that and turn that in the way of construction. And so that's what we're doing here. Okay, so we're saying that whatever is here on this kinematics has to satisfy this to be part of the theory I'm talking. This one cut teaches us a lot for vectors. All right, what it teaches us is this contact term is absolutely necessary. This gauge, so we don't have gauge invariance for anything that satisfies these cuts when I sum it all together, unless I have this contact term. And the gauge dependence must cancel between channels. I can't have my channels pointing in different directions, completely independent directions, in whatever these internal indices I scrambled onto these Fs are. These Fs, as they play with each other, they have to talk between these different channels. That gauge dependence, that individual Feynman rules don't mean anything. Individual graphs don't mean. It's when you combine them to something physical, it means something, right? And that gauge dependence must cancel between channels. In fact, we learned 2 things. I had 4 points. No matter how I assign my contact terms, the colors of these graphs and the kinematics, right? My momentum that was sitting next to my blocks, my kinematic blocks in the numerator sitting next to it, have to obey Jacobi. Both of them, but the colors have to obey Jacobi as well as the kinematic weights. Okay, and so now we've recovered what we actually need to be talking about structure constants in a Lie element, right? Now our Fs, and again, what did we do? We put in linearized, the same linearized gauge invariance, the same thing we demand from Maxwell. We've just demanded this also holds for our 3-point interactions, our 4-point interactions, and we've demanded consistency, right? The states that propagate, right? When I look on shell to see if, is there really stuff there, right? Has to be considered, it has to be the states in the physical states in my theory. Yeah. And out of this emerges that to have consistent interacting massless vectors, they need to be living in this as a gauge theory, as a genuine gauge theory. Yeah, okay, good. So we've written our now we can call it a Yang-Mills amplitude in terms of these color weights, kinematic weights, sitting over these universal propagators, that exist for all of our cubic graphs. And then you just sum over the permutations. Great. You do the same thing for gravity. Again, you see that this contact is necessary. And it's completely fixed. You completely satisfy both factorization and linearized diffeomorphism invariance by taking your gauge theory amplitude and replacing your color weights with another copy of your kinematic weights. All right, so here too, so we saw this at 3 points that by stripping off color from the gauge theory, replacing it with the, so all it had to do there was anti-symmetry. We saw that lifting gauge invariance to linearized diffeomorphism. And we're seeing this now again in the context of also satisfying Jacobi. We're lifting something that satisfies linearized gauge invariance in each factor. So when we put them together, now it's satisfying a linearized diffeomorphism.
But there's something very basic I'm confused about. So let's say 2 plus 1 dimensional gravity. What is the gauge group?
What is the, I don't know what the gauge, so it has to satisfy linearized diffeomorphism. That's what it has to satisfy. 3 plus 1, 4 plus 1. Any dimension that has to satisfy linearized diffeomorphism.
Right.
And I'm saying that you can construct the amplitude that satisfies this. So again, you didn't need to do this at all. You could have just taken your Legos, put them together, shaken, and says, what satisfies linearized diffeomorphism? And you will find it's unique. It's actually completely unique, right? After you go into a basis of like momentum invariance, right? It's completely unique. And you can get there instead of playing that game of, write down the most general ansatz. You are satisfying that by taking a gauge theory kinematics.
No, I understand what you're saying, but there's this also, at least in lower dimensions, rewriting of Einstein's gravity, presence of cosmological constant in terms of gauge theory. For example, in 2 plus 1 becomes 2 copies of SL2R. But that doesn't generalize to higher dimensions, of course. In 4D, we struggle to write something gauge invariant, right?
Yeah.
This is, even though none of that works, still at the level of the amplitudes structure of gauge theories. So they're
well, and and this is I'd love to come back to this because I don't know in general what this kinematic algebra is that's dual to the color algebra, right? And if I knew that, that would make my life a lot easier. So then I could just write down the structure constants and just go, right? But just because I don't know what that doesn't mean it's not there. It is there, and we can exploit it to make our lives a lot easier and also draw sometimes surprising parallels at the level of a duality, whereas gauge theory has always been sort of like gravity, right? Maxwell is sort of like Newton, right? But this makes it very sharp.
Right.
Yeah. And we see this at the level of classical solutions. Right. And so there's classical solutions you can do quantum mechanics around, right? So there are a lot of ways of using this. All right, so I'm gonna, yeah. Okay, cool. All right, so what did we see? What did we see so far is that, at 3 points and 4 points, for non-vanishing, so for non-vanishing amplitudes at 4 points, we were absolutely required to add a contact term for the gauge theory. There's no additional contact needed, higher multiplicity for Yang mills. So you keep doing this, imposing gauge invariance and factorization completely fixes it. There's no contact terms, or indeed imposing this duality between color and kinematics and factorization completely gives you gauge invariance. So as you're bootstrapping forward, choosing what there's a limited set of things you're imposing, and you get the others for free. Okay. Every higher multiplicity gravity amplitude, as I think you all know, when you expand root minus GR, you have an infinite set of contact terms. These are absolutely required for the linearized diffeomorphism of the theory. And order by order, it's encoded by the double copy of gauge theory amplitudes when you've written this in a color dual way, when you make this kinematic algebra manifest at the level of on-shell amplitudes. And so you can say, oh, how does that work? I've only got, I've got my 3 point, my 4 point contact. How do I get 5 point contact, 6 point, and 7 point contacts in the gravity theory? And it's by cross terms in this double copy. So I'm just going to show you how that how that shows up, because it's actually instructive and cool. All right, and because this is a very amplitudes forward way of talking about what operators are doing anyway, right? And so what do we need the operators for? We need our operators to give ourselves the correct predictions. Yeah. And so at any multiplicity, any quantum field theory, multiplicity, number of particles interacting, right? There's an occasion for novel theory information not present at lower multiplicities. And this is novel contact information, right? So the new contact with the M fields interacting, plus all the stuff you can reconstruct from cuts from the lower multiplicity amplitudes you have, right? So of course you can just grab this contact information by taking your amplitude and subtracting off all the cuts. Yeah. And you can just promote this. You can just promote this to your operator in some representation, right? And I'll talk a little bit more about that later. But hopefully, just as you see, it's a very mechanical process to go from actions to amplitudes, right? It's laborious, but it's mechanical. It's just as mechanical process to go from unique contact data to operators that produce it. Okay, good. So I'm just going to show you. I think you're probably all with me on how to. So how I've written the kinematic weight associated with my cubic graph, my trivalent graph, right? In terms of something that comes from, something that had no contact terms. Oh, and this is something that's absolutely true, right? So what's sitting here in the propagators are just momentum invariance, scalar momentum invariance. I can always choose a basis to make the propagators, the inverse propagators, part of my basis. So I can just expose what they're doing in the kinematic numerator, right? And so you can say, oh, who's sitting next to, an S12, right? Who's sitting next to this guy? Who's sitting next to an S45? And then who's sitting next to both? Right, and it's this guy that's actually contributing our contact information, our unique contact information here. And we can just get at it mechanically by subtracting cuts from our numerator. So a graph like this contributes to 3 cuts. It contributes to cuts where you cut both propagators, a cut where you cut one of the propagators, and a cut where you cut one of the other propagators. Right, and again, in some sense, this is just bookkeeping. Right, but this is bookkeeping, tracking the novel information that's showing up at a particular multiplicity. All right, I hope it's clear that subtracting the first cut from the second gives you the contact information, associated with that one guy, and the first guy from the third gives the other contact, right? So you can recursively isolate the novel 5-point contact. And just mechanically subtracting away data. Yeah? Okay, good. So let's talk about the kinematic weight of gravity. So I've written my gauge theory kinematic weights in a way that satisfies this duality with color. So I'm making manifest that it also satisfies this function, polarization, momentum, satisfies Jacobi identities and anti-symmetry. Yeah? Now, gauge theory, even the color dual representation isn't manifesting like spurious contacts at 5 points. So there's only 4-point contacts living in the theory, right? There's no 5-point term. Yeah. My double copy, of course, what I get is the parts that I have the cross terms. Yeah. So you see, so it encodes the 5-point, it's literally the 5-point data, the 5-point contact information required by linearized diffeomorphism invariance at 5 points. I need to add more data to my theory than what I had from lower multiplicity, right? But it's entirely contained in the double copy of the gauge theory. All right, any questions about this? All right, and this goes on to all interactions, all multiplicity, provable at tree level. You can always do this. You can always have, and constructively, you can make representations that manifestly satisfy duality color kinematics, and double copying uniquely gives you the gravity amplitude. All right. Okay.
Sorry, if
Yeah.
you just generalize this allowing for higher derivatives, you just get the tower of higher derivative corrections as you are. Is that the idea?
Yeah. I'm going to talk a little bit about higher derivative corrections in a bit. So, but yes.
There are no consistency relations between their coefficients, right? It's just you get three terms as two derivative, as higher derivative, as R squared. Right, okay.
Right. So there are. Let me talk a little bit more about higher derivatives in just a little bit, but yeah, let me make it a little more again. I could just detour right now, but okay, good. I just wanted to emphasize that, of course, I can write the operators level of my action. So I mean, again, like I had every right to be writing the free operators, like free quantum operators, right? Accessing the sort of dual space, right? Vectors, right? And we can see manifestly, I can construct these gravitational operators that are living, that's speaking to these two spaces. All right, and so so this is actually just this is something we put out pretty recently. There's something very so establishing that the color weights between graphs are related means that the number of distinct color weights you ever have to write down at any given multiplicity or loop level is very small and very limited. You've got Casimirs, everything's just nice and small, right? A small basis. The same thing for the kinematic weights, and when you impose automorphism symmetry, that doesn't matter which way I dress the graph, right? It has to yield the same information. Then there's a drastic reduction. It turns these Jacobi identities, if you were going to solve it with an ansatz, into solving functional relations, not algebraic relations. And this is what we have to do when we're making this manifest at the integrand level, the multi-loop level, right? But that it means that the basis of topologies you ever need to dress is very small, and then these algebraic relations propagate them out to the full amplitude. Now the reason this is important, I'll point out for scattering amplitudes folks, is that scattering amplitudes don't grow with a power law or exponentially, they grow factorially in terms of the number of graphs that contribute as multiplicity or loop level decreases. Having something that battles this combinatorial explosion is actually incredibly efficient. Good. Cool. So yeah, I was just going to sketch, so, so I'm talking about things in terms of things that are kinematically dual to this antisymmetric adjoint FADCs. And there are tons of theories. Some of our favorite theories, like nonlinear sigma-model pions or Born-Infeld photons. So the first avatar we ever saw of double copy was actually in string theory amplitudes at tree level in the late 80s. Henry Tai and his buddies Kwai Llewellyn and Tai realized that you could write down the tree level amplitudes for closed superstrings as the terms of sums over products of various permutations of color ordered, champagne ordered open superstrings. There's a lot to unpack in that sentence. But this was the first reference, and what this meant was that there were relations, if you take alpha prime goes to zero, there are relations between Einstein gravity amplitudes and and these color stripped or color ordered gauge theory amplitudes. And what does that mean? What does that mean? So when you write down, when you just use Feynman rules, you start writing down your Yang-Mills amplitude, you've got your color directions pointing every which way, but of course, there's redundancy between them. Yeah, and so you go into a basis. Whatever's sitting next to that basis has to be gauge invariant. If I'm going, once I've exhausted all the algebra, maybe it's going to a trace basis, maybe it's just, solving the Jacobi relations to the color. Whatever's sitting next to it after I've gone to a minimal basis, whatever kinematic's next to something that's pointing in an independent direction color has to be a gauge invariant building block. It has to be. You can't speak to anybody else pointing one direction. That's what people call color ordered amplitudes. Okay, anyway, so one of the big surprises over the past 15 years is not that closed superstring amplitudes obey some sort of stringy generalization of double copy. That's where we started. The surprise was that open strings and closed strings you could write as double copies with an effective field theory that carries a scalar effective field theory that carries all order of alpha prime information and normal gauge theory stuff, right? That was a surprise. And it's what that means, of course, is that we have every right to play around with these tree level amplitudes with this. We can think of string theory as like the simple harmonic oscillator of non-local effective field theories, ones that are completely consistent, that are under control, that we have a right to know about. We can start building field theory tools for how to handle these guys, right? And so there's something super fun about that. Anyway, there's this whole web of theories but with a very small number of building blocks, that you put these predictions together in different ways, and you're getting predictions in different theories. Oh, there's a cool trick. There's a cool trick to make your operators look like amplitudes, because that's where some of this structure is beautiful, right? I mean, that's where these things are very chematically beautiful. And this is a trick from Deroux, which is just to introduce separate coordinates for each field and then integrate over delta functions that collapse them, right? So you're going to be manifestly local after you do the integral over your delta functions. This lets you just target your different fields with your derivatives. So it manifests the same sort of kinematic structure in a way that is very useful if you want to see this kinematic algebra showing up prediction by prediction. Good. I should mention related work, that there's a ton of different approaches to taking gauge theory information and either organizing it so you make structure manifest in the amplitude, or writing gravity in terms of gauge. I think the closest in spirit is this 99 paper from Zwieburn and Grant, where this was long before we recognized this graphical Lie algebra governing the kinematics. So all we had access to was the alpha prime goes to the zero limit of string theory, these KLT relations or momentum kernel relations, order information. But even then, it was clear by looking at the amplitudes, you could extract out the contact information and then write ansatz, say, in your action to reproduce it, and then grab the smallest ansatz in your action that reproduce it. And that's what they did. It's a really cool paper. And I'd say like way ahead of its time. All right, so anyway, this points to a direct operational approach to quantum state level double copy in terms of what I've talked to you about, at the order of semi-classical effective actions. But of course, there's nothing that prevents you from doing this again with your multi-loop integrals, building up your quantum effective action, right? Every place you can make the structure manifest. I emphasize the type of stuff I care about, which is color kinematics and double copy. But there's all sorts of structure and all sorts of theories, right, that we discover when we look at their predictions, and I think making that as manifest as possible in terms of how we talk about our theories with each other is very useful. And so I'm hoping that this can serve as a bridge between communities, especially communities that don't actually speak amplitudes very frequently. How am I for time?
In 20 minutes?
Oh, great. Okay, cool. So I have a little bit more that I'd like to share, and then go into a free discussion. All right, good. So, as I pointed out, many theories are double copies, manifest as double copy structure with antisymmetric adjoint FABCs. But even for Yang-Mills, we know that it's not just FABC, it's FABC at tree level, but the second we start doing loops, we start getting symmetric structure constants showing up, right? We have other structure that is important to represent if we want to capture all the higher derivative operators that one could ever write down. Yeah?
So what's the theory?
Oh, good. Okay, so this is the scalar theory. This is the scalar theory that lets you go between field theory, gauge theories, and superstring and string theories, heterotic string theories, bosonic string theories, open and closed. So the disk integrals that show up, when you're writing down open string theories,
Yeah.
they have two orderings to them. They've got an ordering of your integration and an ordering of the integrand. What was discovered by this fantastic paper with Brodel, Stieberger, and Schlaberer was that one of these orderings obeys Champayton string theory relations between ordered amplitudes. That's the order of integration. The order of the integrand obeys field theory relations. Okay, and so.
Oh yeah, we used to have a.
Yeah.
Sorry.
No, maybe I can use, I've never tried this, and I'm sorry if I'm just gonna mangle it. So, all right. Two orderings. So it's a doubly ordered expression. Okay, so take this expression, dress the Champayton ordered, which traces Champayton traces field with with traces from field theory. And you've got a bicolored scale. You've got a bicolored scalar theory. This bicolored scalar theory, one side just has FABCs, the other has a mixture of SCBCs and other stuff, and it's got higher derivative. So if you expand it around alpha prime, then it'd be a tower of higher derivative, or you just you just keep your disk integrals as the resummation. And you can expand around alpha prime going to infinity or zero, right? So it's a non-local effective field theory, but one that's spectacularly consistent, right? And it has the power of string theory behind it. Okay, is that?
Yeah, thank you.
But it's not the only, there are operators you can write down, even for scalars, that don't contribute to this, right? So it's not every operator you can write down for scalars. It's a select special set of operators that are consistent with being able to write it in terms of things that satisfy Jacobian antisymmetry and factorization. And it just so happens, it's also spectacularly well behaved in the UV, right? Okay, good. So let's see. Maybe if I do this, can I start? Okay, good. Oh no. All right, hold on, sorry. I don't want to eat up all my time learning how to use Zoom. Okay, good. All right. So our adjoint FABC, are these types of rules the only way to striate gravity? Pull apart gravity into stuff that has structure. Color is rigid. Color is very rigid, gravity's floppy. Yeah? Is this the only way to pull apart gravity? No. And I think one of the most educational things for me was when this paper came out in 2012, talking about 3D supergravity. So maximal supergravity in 3 dimensions. Of course, you can write it as the double copy I've just been talking about in terms of antisymmetry and Jacobi, in terms of maximal super Yang-Mills reduced to 3 dimensions, right? Great. But the same exact theory, same exact scattering amplitudes, you can write in terms of BLG, Bagger, Lambert, Gustafson, 3-dimensional theories that don't obey a Lie algebra, right? They obey this crazy 3 algebra. Yeah? It only exists in this dimension, right? But it's perfectly consistent. So this same theory is right, the information here, you can pull apart into 2 very, very, very different looking, entirely consistent theories. Yeah? Good. So, so are adjoint FABC rules the only way to strive Bose Fermi statistics? Absolutely not. Oh, okay, good. And so Lance Dixon, who's awesome, used to get really frustrated when I'd introduce I'd introduce either like metaphors or acronyms without ever defining them, right? And so he made me promise that I would always, if I was going to use a metaphor in the shape of an acronym, I would define it in my talk. And so this is a slide where I'm doing that. So as I said, once I impose automorphism symmetry, to get this utility to the multi-loop level, now I'm solving functional relations. And so the question is the only way to handle functional relations, by introducing big ansatz, right? And for a while, since Evanston is where Tinker Toys were invented, these toys, these spindly things you put together in various different ways, right? That I could be very late in getting people my talk titles and then just explain those Tinker Toys beat ansatz, and I put things together the right way, everything's gonna be fine, I can compose solutions. But the thing about the Tinker Toys is they're kind of unwieldy and spindly, so I'm really landing on this Lego metaphor now. And so that stands for local effective gauge operators. All right. And so hopefully Lance is happy with this, but this beats ansatz. And the idea is that when I have things that satisfy functional relations, I can put them together in such a way to satisfy the same functional relations. So as long as I have an instance, then I can start building a ladder to all sorts of other solutions by putting it together in ways that obey the same structural relations. And so all the things that contribute on that capital Shan-Payton side of Z theory, scalars mixed with color to satisfy Jacobian antisymmetry, you can actually get with a small number of building blocks, a very small, that you just compose together and span everything. And so if I have something that's linear in Mandelstems, right? Then if I compose it together, now I've got something that's quadratic in Mandelstems, and I just build a ladder all the way up to the UV. All right, so what makes a useful double copy? And this is the thing, this is why it's really useful to be looking at gauge theories, because gauge theories give you structure. You can do anything to a scalar theory, like anything with scalars. And again, they're fine, but gauge theories, they require gauge invariance. So if I have a way of taking gauge invariance and promoting it to linearized diffeomorphism, right? That's something powerful, right? And if I preserve unitarity locality, if I promote supersymmetry for like n equals 8, right? So, okay, good. And so this is just a laundry list. So I've been really spending a lot of time the past few years thinking about effective field theories and higher derivative operators. And there's all sorts of results and ways of talking about these things. I think to a point, you asked about, all 4-point gauge and gravity operator predictions in arbitrary dimensions are spanned by a small number of gauge building blocks that are either dual to the antisymmetric adjoint, or, and this is something, so like if you were to play this ansatz game with gravity, right, but allow yourself arbitrary dimensions, it's spanned by a small number of building blocks, and then all the permutation invariants, which are, again, spanned by something very, very small at 4 points. So, and so this is where we're putting this out very soon. I'd like to close by acknowledging that data drives important physical questions. We're having access to astounding precision in event shapes and energy correlators, which doesn't give us a direct window into quantum color evolution, because that's very hard given confinement to asymptotic freedom, but it encodes quantum color information. Gravitational wave astrophysics is an increasingly important source of data regarding the classical limit of quantum gravity. And all the techniques I talked about today, unitarity methods, double copy, these are what's going into the highest post-Minkowski corrections to the classical solutions of Einstein gravity that's being used to generate waveforms for next generation detectors. And I should also mention cosmology is an increasingly data-driven source of our most important physical questions involving the quantum evolution of space-time, given the energy scales that are ultimately encoded. All right, and so with that, I think if you notice a twinkle in Albert's eye, might be 2 copies of Yang Mills looking back at you.
Thank you so much. More questions?
At the loop level, you have to eventually need to go and face ghosts.
If I was using off-shelf Feynman rules, I have to face ghosts. If I'm constructing with physical propagators, I do not need to introduce ghosts. It does the same thing as introducing ghosts, right? What are the ghosts there for? The ghosts are there to eat up the unphysical information that I introduced with my off-shelf Feynman rules. They're mandatory there. Yeah, but no, this is a unitarity construction. You can think of as a perturbative quantization that really lets you start with the degrees of freedom you want and maintain. Yeah, that was a good question.
Follow up on that, the reason that we end up with some physical degrees of freedom is that we insist for a local action for a theory that has non-local degrees of freedom.
Yeah.
Now, this formalism of amplitudes tells you that, well, at the level of the amplitudes, we could just completely forget about these physical degrees of freedom and talk only physical all the time. Does that shed any light on whether, like, I made two statements.
Yeah.
What is there to learn?
Yeah, so I'm okay, so I'm gonna answer this in 2 ways. All right. So the first time I ever talked about this, the sort of the way I just talked about this, was at this amplitudes after party in Taiwan this past summer. So a bunch of amplitudes people, very happy to have a successful conference in Korea. Now they're in Taiwan having a great time. And I told them, hey, you know what? Let's take all this rich data, rich structure we find, and let's go back and write down actions, right? And half the room's like, what? We've been doing everything we can to get rid of actions, right? To get rid of, and it's fine, right? Because there is a way to live one's life and build entire careers where you're not talking about local stuff at all, but you're just talking about structure yeah. Now, that's I think that that's a very balkanized way of looking at science. And I think there's one of the things amplitudes as a community is pretty good at like speaking to people who live, you know, string theory, mathematics, cosmologists, and so. And there are many insights to be had by looking at things in complementary ways. I think this is an attempt to bring some of this back towards looking at local structure, but I'd say that's in very early days. And I think that there's still a lot to learn.
Any last questions? Not, let's thank John.
Thank you so much. This was a super clear